Welcome to lecture number 9 for ECE 320, Digital Electronics. Today we're going to look at diode circuits and ways to implement circuits that find the maximum of a set of voltages, the minimum of a set of voltages, or the average of a set of voltages. Now the reason for this is one way to implement fuzzy logic. Now fuzzy logic is a degree of mathematics that handles statements which are only partially true. For example, suppose I wanted to find how fast a car is going. I could say fast is defined as you're going 50 miles an hour. Medium if you're going 30, slow if you're going 10. Well, what happens if you're going 35 miles an hour? And you're not exactly 100% true that you're going fast or medium or slow. How do you handle that? Well, fuzzy logic is a way that lets you handle that. For example, I might define slow to be 100% true if I'm going less than 10 miles an hour. The degree of truth drops as I go up to 30 miles an hour, then 0% true if I'm going above 30. Medium might be 0% true if I'm going less than 10. The degree of truth goes up to 100% true when I'm going 30 miles an hour, then dropping. And fast would be the blue line. That way if I'm going 35 miles an hour, it might be 70% true that I'm going medium speed, 30% true that I'm going fast. And where this is useful is this lets you come up with things like fuzzy logic. Now fuzzy logic was started by Lofty Zeta, and what he was looking at is how do you design or how do you model the behavior, let's say, of an expert subway driver. Now what a subway driver does is they don't take the speed and go full speed forward, full stop. What they'll be doing is implementing a set of rules, such as if I'm going down the road or say if I'm driving, the roads are clear, it's a good day, the roads are in good condition, I can see far, I'm far away from the next turn, I'm far away from the city, I'll drive fast. However, if I'm approaching a turn or approaching a town, I'll slow down and go medium speed. If I'm driving by a school, drive slow, and so on. So you can come up with all these sets of rules. And what Lofty Zeta was looking at is, can you take, say, a subway driver, figure out what an expert subway driver is doing, come up with a mathematical way to describe that, and then implement that. That way every subway would be driven as if it was driven by an expert subway driver. But to do that, I don't have things being Boolean logic. It's not either full forward, full speed fast, or slow. What happens is, as you're going through the countryside, I'll be going fast. As I come towards the city, I'll gracefully slow down. And then when I leave the corner, leave the city, I'll gracefully speed up. How do you do that? And that's what fuzzy logic was geared for. So that was the goal, and if you can come up with a mathematical way to describe it, I can implement those sets of rules. Now today, fuzzy logic actually has quite a few applications. It's being applied for aircraft control for spacecraft, vacuum cleaners, washing machines. Again, like with a vacuum cleaner, what I might want to do is set the power or suction based upon how dirty it is. If you're cleaning up the cat's litter box room, I need a lot of suction. There's a lot of dirt coming up. If the carpets are pretty clean, I may not need to do quite as much. Or washing machines. If there's a lot of dirt in the clothes, I might want to change how I do the cycle versus if the clothes are fairly clean. It's applied in automotive for idle speed control, personnel evaluation, underwater target recognition. Now, these are all examples of things where it's not Boolean. I've got kind of degrees of truth. Things are partially true. And in Japan, fuzzy logic is kind of the rage. It hasn't quite caught on in the United States, and it might be the name fuzzy. In Japanese, fuzzy means clever. In the US, fuzzy means blurry, and who's going to want to buy a fuzzy TV? But, it's just a word. It's another way of implementing things where you don't have to do things full on, full off. I can sit there and vary how you control it. So if you recall from digital system design, I can implement any logic using and, or, and not. And what I want to implement is a bunch of if statements. Like the example we had for a subway driver or driving your car is if you're far from a town and the road conditions are good and it's sunny outside, then drive fast. Well, I need to come up with a fuzzy definition of and, or, and not then. So let's start with Boolean logic. In Boolean logic, A and B are true only if both A is true and B is true. Now, a consistent way of implementing that is to say that A and B is the minimum of A and B. So if either one is 0, the minimum of A and B is going to be 0. The advantage of that definition is it can handle partial truth. For example, if I say A is 70% true, B is 30% true, what is A and B? Well, taking the minimum of A and B is 30, 0.7 and 0.3 is 0.3. So that's a consistent definition of AND. Let's look at OR. The truth table for OR is that either A or B is a 1, the output is 1. And again, this is logical OR, not English OR. In English, when I say A or B, it kind of implies not both, such as either I'm going to the store or you're going to the store. That sort of implies we're both not going. So English OR is actually exclusive OR. This is logical OR. With logical OR, that would be A or B or both. Now, a consistent way of implementing this, interpreting this, is that either one's a 1, the answer is 1, or I could also say that this is a max function. Take A and B, take the maximum of them. That's the answer. The advantage of that definition is that it can handle partial truth. For example, if A is 70% true, B is 30% true, then A or B would be the maximum of them. So 0.7 or 0.3 is 0.7. And a not function is 0 goes to 1, 1 goes to 0. A consistent definition is not is just 1 minus A. So not 0.7 is 0.3. So with that, I can now do and or not. I can implement almost anything with fuzzy logic. Now let's look at the hardware. Come up with a hardware circuit to implement a max function or min function, and we'll also look at the average. So a max function is actually a diode circuit. If I have a bunch of diodes in parallel, this will pull off the maximum. And the way to figure that out is, some people like to memorize if the diodes face right, it's the maximum, face left, it's the minimum. I don't like doing that, partly because my memory's not that good. But also, as you redraw the circuit, it gets confusing. What I like doing is, given a circuit, figure out which diode is on, which one's off. And it's going to be one of the extremes. It's either going to be B or C. One of those two is on. Let's assume for a second that C is on. I have a 0.7 volt drop across the diode that makes this 1.3 volts. Does that work? Well, if this is 1.3 volts, then B also turns on. And 7 minus 0.7 makes this 6.3. The voltage on the right can't be both 6.3 and 1.3 volts. If I build the circuit, it's not going to get confused. A circuit with diodes and resistors is too dumb to get confused. So that's just not possible. So that means my assumption was wrong. C is not on. Let's try the other diode. Suppose B is on. In that case, I lose 0.7 volts across the diode. Y becomes 6.3 volts, and that works. I've got 6.3 going to 3. That's trying to force current backwards through A. A turns off. 6.3 to 2. Force current backwards through diode C. It turns off. And this one turns off. Only one diode could be turned on, and that's what I have. So there's the answer. R doesn't really matter. This can be anything you want. Diodes are current devices. I need to have some path for the current to flow. And as long as the current's flowing, for an ideal diode, it's about 0.7 volt drop. So this just allows some current to flow in the device. That's a max function. I can check that in Circuit Lab. So if I have this, let's have, say, 3 volts, and this is a sine wave, offset is 5 volts, 5 volt peak, so this will sweep between 0 and 10. This is a max function. What should happen is, excuse me, I'll pull off the maximum of 3 and my sine wave. So in Circuit Lab, if I simulate that, let's go under Simulate, look at V1, V2, and V3, or Y, run it for 2 cycles, and make it for 2 milliseconds. The step size is 1,000 times smaller. Let her rip. Here's what I see. So this is your V1 in orange, V2 in blue. The output, the brown line, is the maximum of them. Your minus 0.7 volt drop across the diode. So when V1 is bigger than V2, I follow V1. When V2 is bigger than V1, I follow V2. There's your maximum. And to illustrate that, let's change this to, say, 7 volts. Try it again. Again, it takes the maximum. When V1 is bigger than 7, I follow V1. When V1 is less than 7, I follow V2. That's the maximum. A min function, also logical and in fuzzy logic. A min function would be just flip the diodes. So in this case, if I flip the diodes, I've got to change the resistor. Instead of going to ground, it goes to 12 volts. The reason being is these are current devices. I've got to have something trying to push current through the diode to turn it on. And again, it doesn't matter what R is. So again, it's going to be one of the extremes. Let's assume that C is on. If diode C is on, I have a 0.7 volt drop across the diode, anode to cathode. That makes this 7.7 volts. That doesn't work because if this is 7.7, then A also turns on, B turns on, C turns on, and the voltage gets confused. Again, the circuit is too dumb to get confused. It can't be both 7.7 and 2.7 volts. If I build it, it will be something. So diode C isn't on. Let's take the other extreme. Suppose diode B is on. In that case, I've got 0.7 volt drop across the diode. Makes this 2.7 volts. That works. I've got 6 going to 2.7. Current's trying to go backwards, so this diode turns off. 7 to 2.7, this one turns off. 3 to 2.7, that turns off. All the diodes are off except for one. That's what I want. When you have diodes in parallel, only one of the diodes can be turned on. And it's B, so that pulled off the minimum function. Again, in Circuit Lab, I can check that. Get the right circuit. If I flip the diodes, and I've got to change this guy and go to 12 volts rather than ground. Doesn't really matter what R1 is. Let's change this to the ones we have in lab, 4004 diodes. Really, all diodes behave about the same. Doesn't make a huge difference which diode you choose. Now V1 is 5 volts, V2 is a sine wave. Again, 5 volt DC offset, 5 volt peak, so this is going to sweep from 0 to 10 volts. This will be a min function. When V2 is less than V1, I'll pick V2. When V2 is bigger than V1, I'll pick V1. So simulating that, let's go in Circuit Lab, do simulation, run it for 2 cycles, 1,000 points, let it rip. And here's what I got. Again, it's a min function. When V1 is less than V2, I follow V1. When V1 is more than V2, I follow V2. So it picks out the minimum of V1 and V2, plus a 0.7 volt offset for the diode. And again, if I change this, let's make this 8 volts. Run it again. Again, I take the minimum. Whenever V1 is less than 8, which is most of the time, I follow V1. When V1 is bigger than 8, I follow V2. Along with the 0.7 volt offset. So that's a min function. Now I can build max-min circuits. So for example, suppose I want to do A or B and C. Implement that using fuzzy logic. What that would be is B and C would be min function. So that'd be the diodes going left. Find the minimum of B and C. Take that answer, call it X, find the maximum of X and A. Again, OR is a maximum function. So I'll have diodes going right. And again, I have to have something providing current over here, something sinking current over here. So if I have this circuit, find the voltages and currents that'd be the analysis part. Well, what I'll do, I'll start over here on the left. I've got 10 volts and 8 volts. Again, if your memory is better than mine, you know which one's turned on. Otherwise, we'll just guess. Let's guess that B is turned on. That makes that 10.7 volts. 10.7 gives you a 2.7 volt drop across that diode. It also turns on. That doesn't work. I can't have both diodes turned on. So A is turned off. B is turned on. I have a 0.7 volt drop across it. Makes this 8.7 volts. I now compare 8.7 and 6. Assuming this one is turned on, I'll have 8.7 minus 0.7, 8 volts. 8 is bigger than 6, forcing current to go backwards through this diode. It turns off. And I got lucky. I guessed the right one. So that should be the voltages. To find the currents. The check is the currents have to be positive on diodes that are turned on. So I've got 12 going to 8.7. That is 3.7 volts across 1K, 3.7 milliamps. I've got 8 volts going across 10K and 100K. What is that? 8 divided by 10,000 gives you 880 microamps, or 0.88 milliamps. That works. ID3 is positive. This 3.7 milliamp splits. Some of it goes right, the rest goes left. 0.88 goes right. The remainder, what is that? 3.7, 2.82 milliamps goes left. And that checks. The diodes that are on have positive current flow. The diodes that are off have less than 0.7 volts across them. They actually have negative voltage. This is also where an idea of loading comes into play. Suppose I took this load resistor and made it smaller. As it gets smaller, this 0.88 milliamps goes up. Everything's fine up until ID3 becomes 3.7 milliamps. 3.7 is all I have to play with. Once I consume all that current, then diode 2 turns off, and this is no longer a max-min circuit. That's the idea of loading. If I draw too much current, the circuit doesn't work. Or if I load it too much, the circuit doesn't work. All I can take is 3.7 milliamps. More than that, again, then the diodes turn off. So here's what you should have for the resulting voltages and currents. And this is kind of what you can expect on the quizzes. I'll give you the circuit, figure out which diodes are on, which ones are off, figure out the voltages. Once I figure out the voltages, find the currents, and hopefully the currents balance. Current in equals current out. I've got 3.3 milliamps in. I've got to have 3.3 milliamps out. I've got 0.88 milliamps in. I've got to have 0.88 milliamps out. In this case, this is 0.8 milliamps. This one's 0.08 milliamps. Currents balance. Current in equals current out. So here's the Handheld problem. Find the voltages and currents for this circuit. And let's pause the video, try to solve that, and then we'll pick it up and solve that. Okay, so if you've had a chance to solve the circuit, let's figure out what the voltages and currents are. Let's start out with the voltages. I've got two diodes in parallel, only one of these is on. So let's assume the 8 volts is on. I lose 0.7 volts across this diode, making this 7.3 volts. Does that work? 7.3 versus 4 pushes current backwards, so this one diode turns off. That works. Let's take the diodes over here. I've got 6 and 2. Let's assume the 2 volts is turned on. That makes this 1.3 volts. That doesn't work because C will also turn on then. So D isn't turned on. 6 minus 0.7 becomes 5.3 volts. That works. 5.3 turns off diode D. So the voltage on the right is 5.3. Voltage in the middle then is, let's assume this diode is turned on. 7.3 plus 0.7 becomes 8 volts. 8 to 5.3 is more than 0.7. They both turn on. I can't have both diodes turn on. So that doesn't work. Let's assume this diode is turned on. I have 0.7 volt drop across it, making this 6 volts. And that works. So those are your voltages. Now let's find the currents. 7.3 volts at 1K is 7.3 milliamps. 5.3 at 1K is 5.3 milliamps. Over here, only one diode is turned on, so current through A is 7.3 milliamps. I've got 4 volts at 10K, gives you 0.4 milliamps. That current has no place to go except right. It has to go through this diode. That's 0.4 milliamps. The total is 5.3, meaning I'm missing 4.9 milliamps. That's got to be this current right here. That has to be 4.9 milliamps. So the total is 5.3 milliamps. So those are your voltages and currents. This again is where loading comes into play. This 10K resistor, if I made it smaller, say, if this is smaller, so this current's more than 5.3 milliamps. Once this is 5.3 milliamps, then I don't need any current from C, and that diode turns off. So this has to be big enough so I have less than 5.3 milliamps flowing through the 10K, allowing the extra to come through C. Again, diodes are current devices. For them to turn on, they need to be supplying some current. And in MATLAB, or Circuit Lab, you can check. So here, I built the circuit in Circuit Lab, and what I expect is 7.3 volts, 6 volts, and 5.3 volts. If I run it in Circuit Lab, so you can see what I'm doing, let's do simulate, just do DC, and look at all the voltages and currents, run, here's what you get. So V1 is 7.3 volts, Circuit Lab says 7.315. I calculate V2 is 6 volts, 5.907, and 5.3 volts, 5.330. Again, the calculations are a little bit wrong because I assumed ideal diodes. Diodes are not ideal. They're almost ideal, but a little bit different. So likewise, the voltages should be close, but a little bit off. In terms of the currents, I calculate the current through A is 7.3 milliamps. Current through A is 7.315 milliamps. I expect B, diode 2, to be off, and it's 76 picoamps. So that is nano pico, 0.0000007 milliamps. Yeah, negative. There is a little bit of current going backwards, but pretty darn small. That's 10 to the minus 12 amps. We can't measure that in lab. We don't have the equipment that can do it. I expect diode 3 to be off. Again, it's picoamps, basically off. Diode 4 was supposed to be 0.4 milliamps. Diode 4 is 0.409 milliamps. Diode 5 was 4.9 milliamps. Diode 5 is 4.921 milliamps. And diode 6 is picoamps, basically off. So that checks. So that's kind of a max-min circuit. With that, you can implement fuzzy logic. Another circuit to look at is the averaging circuit. Like, let's find the average of a couple voltages. Well, that actually isn't a diode circuit. That's a linear circuit. With linear circuits, you can just use resistors. For example, let's find the average of 4 voltages. What I could do is just use a 10K, 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 10K resistor. Then by symmetry, Y is the average of A, B, C, D. And I can see that. Write your voltage node equation. It's this current, Y minus A over RA, or 10K, Y minus B over R, plus Y minus C over R, plus Y minus D over R, has to balance. Multiply by R to clear them out. And then Y is just the average of A, B, C, D. So that's the averaging circuit. Suppose I want A to have a weighting of 2. Double weighting. Well, what I can do then is just take A, have it in there twice. Now this is the average of A, B, C, D, or 2A. Well, R in parallel with R is the same thing as, let's get rid of these. Same thing as R over 2. And that'd be the same thing as having double the weighting. Suppose I want A to have a weighting of 3. In that case, I could just have A in there 3 times. So now this is the average of A, B, C, D, or A's got a weighting of 3. Well, 3 R's in parallel becomes R over 3. So essentially what I can do is have the weighting scale the resistor. That's the weighted average. So, with that, this is one application of a weighted average, or an averaging circuit. Suppose X is a minus 10 to plus 10 volt analog signal. So you're going from minus 10 to plus 10. What I want for Y is a signal that just goes 0 to 5. The reason I might want to do that is on microprocessors, something we cover in embedded systems. Microprocessors can only handle voltages between 0 and 5 volts. So I want to come up with a circuit to take my actual voltage and scale it to the range that the microprocessor wants. I don't really need an op-amp for that. I can do that with resistors. Essentially what I want is that Y is 1/4 of X. This has got a 20 volt spread. This has a 5 volt spread. So take that spread, divide by 20. Then take the extreme. When X is 10, I want Y to be 5. So 10 over 4 is 2.5. Plus 2.5 makes it 5. That also works at minus 10. Minus 10 gives you minus 2.5. Plus 2.5 gives you 0. So this is where 10 comes to. This is where minus 10 comes to. Or the midband voltage, when the input is 0, I want this to be midband 2.5. So that's the function I want to implement. Y is 1/4 of X plus 2.5. Well, that's a weighted average. So let's take X. Now let's assume I've got 5 volts available and 0 volts available, and X. What I want to do is put this over a common denominator. 1 times X plus 2.5 is 1/2 of 5 volts. So 2 times 5 volts, so that gives you 1/2 of 5 volts. And that's the function I'm trying to implement. The problem is, for a weighted average, I want the weightings 1 and 2 to appear down here. So 1 plus 2 is 3. I'm missing a 1. So what I could do is have a 1 times 0 volts. So 1 plus 2 plus 1 is 4. That's my weighted average. So the 5 volts has a weighting of 2. X has a weighting of 1. 0 volts has a weighting of 1. Well, what I can do is pick your favorite resistor, like 10K. X comes in with a weighting of 1, so 10K over 1. 0 volts comes in with a weighting of 1, 10K over 1. And then 5 volts comes in with a weighting of 2. That's 10K over 2, which is 5K. So this circuit right here will convert plus minus 10 volts at X to 0 to 5 volts at Y. That's a weighted average, one application of it. Or another way to draw it, same thing. If I have the 5 volts going up, ground going down, here's my signal on the left, this circuit will convert plus minus 10 to 5 volts. Again, that's not really a diode circuit, that's just a resistor circuit. Weighted average I can do with just resistors. And that's kind of useful when I typically, for microprocessors, I want to convert one signal to another one. So, in summary, with diodes, you can determine the maximum of N voltages. That's one circuit, a max circuit. I can determine the min of N voltages. And with that, I can build or implement fuzzy logic. That'd be doing these ands and ors. But each time I do that, I lose 0.7 volts. I think on the and, I lose 0.7 volts. On the ors, I gain 0.7 volts. So it's not perfect, but it's a quick and easy way to implement logic. It's also really, really fast. All I have to do is charge the capacitor and the diodes. Again, diodes are inherently capacitors. If I have a PN junction, I've got this depletion zone with plus charges on one side, minus charges on the other. So it takes a little bit of time to charge up a capacitor, and all diodes are inherently capacitors. They're not real big, but they are there. So likewise, the speed isn't infinite, but I can typically implement fuzzy logic on the order of nanoseconds. And that's lecture number 9 for ECE 320, max, min, and average circuits.